Okay, welcome to another fabulous day in Calculus 3, and we're continuing our journey through Green's theorem. So just a reminder, what did Green's theorem say? So here's Green's right here, and it says, here, I'll be green, woo! So if you've got a simply connected region, piecewise smooth boundary C, which is your curve, your path, and it has to be oriented counterclockwise. Has to be going around counterclockwise, and it's traversed, your border of the region is traversed once. Okay, and if M and N have continuous first partial derivatives in an open region containing R, that would be your vector field there. That's where your vector field gets involved. Remember M and N are the components of your vector field in alphabetical order. Okay, so this involves vector fields. And so if you're trying to evaluate either a type 2 or a type 3 line integral, which are both vector field line integrals, either one of those, because they're really the same. If you're trying to do either one of those, you don't have to. If it's a closed curve and all the criteria are met, then you simply evaluate a double integral instead, where the double integral integrand is dn dx minus dm dy. Now, last time I was able to show, after proving it, that we did a verify problem, where the verify, we did the brute force line integral, which means we had to parameterize, and this one was a tough one because we had to parameterize two different curves, and then we had to add the results. And it took us a while. Oh my goodness. We parameterized the other curve. Whew, that was a hassle. And then we did the right-hand side. So we actually applied Green's. And we found that when we did this, when we did this wonderful double integral, it was a lot easier. It was a lot easier to do. It was quicker after we set it up. And we found that, we love Green's. Yeah. So we're going to do some more problems involving Green's today. So I hope you can appreciate the fact that Green's is definitely the way to go. Okay, here's a question. Does a vector field need to be conservative in order for us to use Green's theorem? Yes or no? The answer is no. Now, if you are going to use the fundamental theorem of line integrals, that's a different story. Then you have to have a conservative vector field. But Green's, no way. In fact, if you have a conservative vector field, you don't even really need to apply Green's. Well, why not? Let's look real quick, because look, here's Green's right here. What do we know if F is a conservative vector field? What do we know about that? We know that means that dn dx, the partial of n with respect to x, would be exactly equivalent to dm dy, the partial of m with respect to y. So if these were the same thing, what would this expression be equal to? What would dn dx minus dm dy end up being? What would that result be?
0.
0, exactly. And that goes back to equivalent conditions. Remember when you have a conservative vector field and it's a closed curve that you're trying to evaluate the line integral on? Remember the answer is 0 for closed curves? Aha. So if you are going to try applying Green's to a conservative vector field, you're actually wasting your time because there's no need. The answer is automatically 0 for closed curves. Okay? So let's look at another example here. We're going to need to apply Green's because it's much easier than doing the brute force line integral. We already found this out. So the region R here, we're bounded by the graphs of y equals 2x. So y equals 2x is a diagonal line. It's got a slope of 2. And then the other, our region is also bounded by y equals x squared. You guys know this is a parabola. And so what is the region of integration? And after having the multiple integration module, I hope you can appreciate that you need to shade in your region to get full credit. And there is your region R in between these two graphs. Okay? So certainly that is a closed curve. And if we consider going around the region in the counterclockwise direction, so, you know, we could start here, say, and then we would go up and we go here, and then we go back down to where we started from. But we don't have to parameterize these two separate piecewise smooth curves. I mean, we could, that would be doing it brute force. I don't need to. I'm going to say that this line integral, which happens to be of differential form, is the same as a double integral over the region where the integrand is dn dx minus dm dy. Yay! So who's the m and who's the n? Well, in differential form, remember, whatever is multiplying with dx is your m, and whatever is multiplying with the dy is understood to be your n. N as in Nancy there. So we're going to do that. Now, dn dx, the partial of x cubed with respect to x, I believe is 3x squared, minus the partial of m with respect to y, looks like it's going to be 5x. And I'm going to choose my dA, my area element, to be my favorite order of integration, which is dy dx. That's the vertically simple. And now I need to iterate my double integral symbol. So if x is the outermost integral, what x values are we going to on this region R? It looks like the lowest x we hit is x equals 0, and x equals 2 is the upper limit. Now, what about the limits for y? Please don't say 0 to 4. You only have all pure number limits when you have a rectangular region where all the limits are pure numbers. This is not the case. So you're going to need to get the little man involved, or if you want to think of it as like a cross section here of this region. And the little man's head is touching the upper limit for y equals 2x. And his feet are touching the lower limit for y, but that's y equals x squared. Okay, so now we're halfway there. We just have to evaluate. So let's go ahead and do that now. We're going to take the integral of 3x squared minus 5x with respect to y. So that's going to be 3x squared y minus 5x y. And we'll go from x squared to 2x. This is going to be a little bit messy, but oops, I forgot my dx. I got to be, still have a dx here. Okay, so now we're going to go 3x. Am I going to need some more room? I don't know. We'll see what we can do here. 3x squared, 2x minus 5x, 2x. Okay, I substituted in the 2x. Minus, now let's go ahead and substitute the lower limit, x squared. So I'll have 3x squared, x squared, minus 5x, x squared. Okay, this whole mess is still going to be integrated with respect to x after we clean it up some. Okay, so let's go ahead and clean it up. So the first term, 3x squared times 2x, is 6x cubed. The second term is 10x squared, and then I'm going to distribute this minus here. Looks like I'm going to have minus 3x to the fourth, and then minus minus will be a plus 5x cubed, and then dx. And this is just a Calc 1 problem at this point, you guys know. I am going to combine a couple of like terms just because I can. Those x cubed terms, I'll combine them. It's a little cleaner. And now I can integrate. So this looks like the antiderivative will be 11/4 x to the fourth minus 10/3 x cubed minus 3/5 x to the fifth, going from 0 to 2. And we'll just wrap it up here. I get negative 28/15, and that's the exact answer. And if you had to punch it up into your calculator, it's approximately negative 1.861. Okay, and that concludes that example. Let's take a look at this next example where we use greens to calculate work. What kind of work? Well, the work done by a vector field on an object as it moves around in the vector field. Okay, that kind of work. And you know that you just do the line integral, one of the vector field line integrals. And basically work is the line integral FDR. Or if you've got if you want to do the differential form, work is, the mdx plus ndy thing also. You can use either one. But we're not even going to do a line integral because we know if we have a closed curve, simply connected region, we're not even going to do the line integral. We're going to set up the double integral. Yeah, more fun. So here's the vector field. Y cubed I hat plus x cubed plus 3xy squared j hat. And the particle travels counterclockwise once around a circle of radius 3. And so we can draw the picture of the curve. Okay. We'll assume it's around a circle of radius 3 centered at the origin right there. Going around counterclockwise, fine. So what do we know? That work, even though it might be one of these line integrals, we're not going to do the line integral because we know that this line integral, if it's closed, that's where you put a circle on top of the integral symbol. Pretty cool, huh? That means closed curve. That's the same as a double integral over the region where dn dx minus dm dy is the integrand. That's what green says. Yay, yay, greens. And the region for us is this circle of radius 3. So that's our region. So let's go ahead and get dn dx, knowing that n is the x cubed plus 3xy squared. So what is the partial of that with respect to x? 3x squared plus 3y squared. Okay, minus, now let's go ahead and get dm dy. M is the first component of the force field. That would be the y cubed. If we take the derivative of m with respect to y, I get 3y squared. Now, this problem is kind of cool because the 3y squareds cancel. Oh, nice. Does that always happen? No, but if it does, it's sweet. Now what? Well, come on, we're going to convert to polar. Oh, wait, I thought that was over with. Oh, no, we learned all that stuff in the last module to prepare us for the vector calculus module, which is happening right now. Congratulations. Yeah. And why is it a good idea to convert to polar? Because look, our region is a circle. So it just makes sense. It's a perfect candidate. The region is a circle or a portion of a circle. Boom, convert to polar. So R is going to have the range of 0 to 3. And since it's the entire circle, theta will be going from 0 to 2 pi. So when we take this double integral, it becomes this iterated double integral. And then, of course, we use one of the conversion formulas. X is r cos. So we'll have r cos theta squared. And then remember, the area element for polar is be a pirate.
R.
R. drd theta. R. There we go. Yeah. Yeah, that's the ticket. Now clean this mess up before we integrate with respect to r. This r cos theta squared is going to give us r squared. And if we combine all the powers of r together, we're going to have r cubed. So I'll kind of put it over here. And then we're going to integrate with respect to r. Fine. So we don't need any u sub in this yet. So the antiderivative of r cubed with respect to r is r to the 4th over 4. And we're going to evaluate that between 0 and 3. And that becomes, 3 to the 4th power is like 243. So what we're going to have here, 3 to the 4th, sorry, is 81. But then we got an extra factor of 3 here. So 81 times 3 is 243. So I'm just going to pull out that constant multiple. Now, does anybody remember what to do with a cos squared?
Yes.
Half angle identity.
Yeah. Half angle identity. And we're gonna use
I don't call it
the
the half angle. What do I call it?
Power reduction.
reduction
Power
formula.
reduction
Power reduction.
formula. Yeah, because that's what you're doing. You're taking a power of cosine squared, and you're reducing the power of it. So you're not really applying the half angle formula here in the, you're not having any angles. So that might be a little bit of a misnomer, not because it's the wrong name for that identity, but I'm using it in the opposite direction. Power reduction formula. So what is the power reduction formula for cos squared? I think it's 1 plus cos 2 theta all over 2. And then this half I'm going to pull out. So I'll have 243/8. A little bit easier when I don't have to worry about fractions. And then you're going to use u sub on the cos 2 theta because u is 2 theta and du is 2 d theta. So you need a factor of 2, but don't multiply the front here because you don't want to affect this 1. You only want to affect the second term. So when I do the integration, the antiderivative, is going to end up being theta plus 1/2 sine 2 theta. And we're going to evaluate this between 0 and 2 pi. Now, a sine of 4 pi and sine of 0 is both are 0. So this sine term doesn't contribute anything to the final answer. Only the theta does. And sometimes it happens. So your final answer after reducing is 243 pi fourths. And that's the amount of work done on that particle as it moves around the vector field. And that concludes this example. Pretty good, huh? So are you guys ready to try one?
Let's do it.
Here we are. So this one is not in the course reader. I pulled it out of a homeworks, okay? So you and a buddy are going to do this. You're going to find the work done on an object as it traverses a triangle with vertices. The vertices of this triangle are 0, 0, 1, 0, and 0, 2, with the vector field F of xy is going to have these components, -3y, 3x. Okay, so there's the M and there's the N. Okay, so you're going to find the work done on an object as it goes around this triangle with these given vertices. And, I'm going to give you a hint. Since the path is closed, use greens. Okay, that's your big hint. Okay, I'm going to show you two ways to approach this problem. The standard way, the formal way, and then the sort of let's cheat our way out of this final thing. Okay. Well, when are we allowed to cheat? If you have instructions on a quiz or exam, or you kind of notice that, hey, I don't need to go do this, I will allow it. But all the criteria have to be in place for you to do this cheating way. It's not really cheating. I mean, it's basically using your knowledge of geometry. Okay, let's do it the formal way first. Okay, so way number 1. Did I hit the record yet? Yeah, I did. Okay. So way number 1, we're going to set up the double integral, but if I were you, I would draw the triangle because it's always good to see it. So here's the point 0, 0, and then here's the point 1, 0, and then up here is the point 0, 2. So here is the region of integration, shaded in, there it is. Great. So what does green say? The work done is this line integral, FDR, but we don't have to do the line integral. In fact, if we did, it would be torture because we have 3 separate line segments making up our triangle, 3 piecewise smooth lines, and we have to do 3 separate line integrals by brute force, parameterize each, and add all the results. And it would be kind of a hassle. So it's much easier to apply greens and simply evaluate the double integral on that region. So that's what we're going to do. Yay. Okay. So this region is the triangle. dn dx, the derivative of 3x with respect to x is 3, minus dm dy, but that's negative 3. That 3 minus a minus 3 is 6. Ooh, okay. Does that always happen where you just get a constant? No, but when it does, it kind of makes things easy. So then I'm just going to pull the 6 out in front because, hey, let's face it, it's just a multiple. And then my favorite area element for rectangular is dy dx. That's my favorite. And then what? Put the limits on the integrals that's showing, representing this region here. So x is going from the pure number 0 to the pure number 1. X equals 0 to x equals 1. Now what's y doing? You got to be careful here. You don't want to say 0 to 2 because that's going to be so wrong. Well, how come? Because if you put your little man in here, here he is. The little man's head is touching the upper limit for y, but that has the equation what? Well, you're going to have to figure it out. It's going to be like y equals mx plus b of something. So for now, I'll just put mx plus b here, and we'll figure that out in a moment. And then the lower limit for y is y equals 0, since his feet are firmly planted on the x-axis, which has the equation y equals 0. So how do we get this mx plus b thing here? Come on, you guys know. You have 2 points on a line, so you know the slope is going to be the change of y over change of x. So, woo, how'd that happen? Don't know. So that's going to be, let's take the difference of the y coordinates, 0 minus 2, and then let's take the difference of the x coordinates, 1 minus 0. So I get negative 2 over 1, which is negative 2. And that makes sense because that line does look like it has a negative slope. And then I'm going to use the point slope form that you probably have seen in an algebra class one way or another. And you can pick which of your favorite points you want to use, one or the other. Please don't use both, something. How about we use the point 1, 0? Okay, so y minus the y coordinate, but that's 0, equals m, our slope, negative 2, and then times the parentheses x minus 1. And so this equation, after distributing the negative 2, looks like negative 2x plus 2. Yeah? Did you guys get that? I hope. So then what? So then this negative 2x plus 2 is going to take on the upper limit for y. Now you're ready to integrate. Okay. And what's here in the integrand? You can assume it's a 1. And so when you're doing the integration, what is the antiderivative of 1 with respect to y? Well, it's y, right? So you're just going to go, okay, I've got y here where I'm going from 0 to negative 2x plus 2. Yeah. And then you evaluate that, but that's just going to give you negative 2x plus 2. And then this is an easy calculus 1 integral, right? Everybody can do this, hopefully, no problem. Let's see, the antiderivative of negative 2x is negative x squared, plus the antiderivative of 2 is 2x. And so then I'm going to evaluate this between 0 and 1. And of course, we put 0 in there, we're going to get 0. So this is what? 6 times negative 1 plus 2. But that's equal to 6 times 1. Final answer, 6. Okay. And that concludes that problem for way number 1. Now, is there an easier way to do this problem? There actually is, just because, and this is the key reason why, because the dn dx minus dm dy is a constant, the way number 2, and I'll allow you to do this on a quiz or exam, since you can pull a constant out in front, you know, as we saw here, this 6. So way number 2, I'll just sort of skip to that part. Way number 2, because dn dx minus dm dy is equal to a constant, and for us, that number was 6, we basically had this as our double integral. Okay, but this is, there's a handy fact that you learned in the last module when we were studying the chapter on multiple integrals, that when you have a double integral and the integrand is 1, this represents an area of a region. Well, what's the region? In this case, a triangle. In this case, a triangle. So what am I saying? I'm saying our final answer is going to be 6 times the area of our triangle. And we don't even have to bother doing a double integral because, you know, back in 5th grade, we learned what the area of a triangle is. Really? Yeah, it's 1/2 base times height. Well, what's our triangle looking like? Well, let's go back to our little diagram here. The base, it has a length of 1. I hope you could see that. And it looks like the height of our triangle is 2. Okay, so we've got our base and height here for this triangle. Fantastic. Yeah. And the 2's cancel. And our final answer is 6, which is the same as doing it the long way. And now I want to say that you can do this whenever you end up with a constant and then your double integral just has a 1 in it, because that, as we studied when we first started doing double integrals, that's how you represent area between 2 curves. In this case, it is a nice closed region, right? Now, sometimes your region might not be a triangle, it might be a circle. So then you could go whatever that constant was times the area of a circle, and you use your knowledge of areas of circles, pi r squared or whatever, like so. Is that cool or what? Everybody should be saying this right now. Wow. Nothing. What do you think?
Wow.
Zeke is excited.
Oh.
Zeke says, wow. You tell him, Zeke. Look right into the camera. That's right. What do you think? He is duly impressed. He knows how to do Calculus 3 because he sat in many of my Calculus 3 lectures. I'm not going to make him take the final, though. He just told me he loved me. I love you, too. You're good. Okay, now, so this idea of being able to use the area is going to come up into the next problem. Okay, I love you, too. Come here. So check out letter D. Whoops. We're going to evaluate a line integral, that one there, where the curve is definitely going to be a closed curve, so we can definitely, use green because an ellipse is simply connected. And the ellipse has this equation. Now, I'm going to get this equation into standard form because I like to see that better in order to graph it. So I want a 1 on the right-hand side. So to get a 1 on the right-hand side, I'll divide both sides of this equation by 36. Okay. And then the equation becomes, after doing some reducing to lowest terms, that. So that's the standard equation of an ellipse centered at the origin. So what are the x-intercepts? Well, they're going to be plus or minus square root of 9, which is plus or minus 3. Okay. And then the y-intercepts are plus or minus the square root of 4, which is plus or minus 2. And we're going to assume that we're going around the ellipse counterclockwise. Like that, because that's what you need in order to use greens. So there's our region. Okay, good. Now let's keep going. So I don't want to do a line integral because I certainly don't want to parameterize this ellipse. That would be horrible. So I don't have to because I apply greens, and green says, hey, don't need to do no line integral. Just do the double integral instead over your region. as long as you have an integrand dn dx minus dm dy. Okay, fine. All right, let's go get that then. So m is 2xy and n is x squared plus y squared. So the dn dx ends up being 2x minus the dm dy. Oh, this one isn't going to be that one. We don't even have to. Sorry, I misspoke. 2x. This one's actually easier. We'll get to this one. This is 0. What do we just find? We just found that dn dx was the same as dm dy. What does that tell us about the vector field?
Conservative.
Yeah, it's conservative. Vector field is conservative. And this is a closed curve. So we didn't even have to apply greens. I just wasted all my time. Final answer is going to be 0. Okay. We're going to get to the one with the ellipse here in a moment. But I want it. It's similar. Okay, so the moral of the story to this last problem, and I kind of mentioned that at the beginning of today's lecture, is if you're applying greens to a conservative vector field, you're kind of wasting time because, hey, the equivalent conditions theorem we did last time says if you got a conservative vector field and you've got a closed curve, line integral is equal to 0. But we just showed it is true using greens. Fine. Okay, so now you can answer this question. When evaluating line integrals that involve conservative vector fields around a closed curve, this line integral answer is equal to what?
0.
0. Yep. Okay, now let's do the one I was thinking we were doing, which is another ellipse. This is the same ellipse as before. Same one, plus or minus 3, where the x-intercepts, plus or minus 2, where the y. Here we go. Here's our region. And now, ooh, that looks like some terrible line integral with yucky components. Not to worry. Here's the m, here's the n. We're going to say, hey, I don't want to do this line integral. The curve is closed. I can go ahead and do greens. Fine. Let me see if I wrote the 2. Okay, what is the partial of n with respect to x? And notice, even though it has that yucky exponential in there, when you're taking the partial with respect to x, the derivative of that exponential, since it only has a y in the exponent, it's going to be 0. So dn dx here is going to be 1. Oh, nice. Minus, now what about dm dy? Same kind of thing happening here. When you take the partial of this exponential minus y with respect to y, you're going to get minus 1. And 1 minus a minus 1 is really 1 plus 1. So you're going to get 2. And now you're going to get 2 times the double integral, like so. But this represents an area. Well, how come? Because there's only a 1 inside of the integrand for this double integral. So it's automatically understood to represent an area. Area of what? Well, it's the area of the ellipse. Now, this is the weird part. You may not have had a formula for area of an ellipse. Circles, yes. Ellipse, probably not. Because when I've taught this class multiple times, a lot of people have even told me, hey, that's the first time I've ever seen the formula for the area of an ellipse. Thank you. Thank you so much. Yeah. So here's the deal. If you have an ellipse, and let's use one centered at the origin because it's easier, where the center is just 0, 0. The distance from the center to along one of the axes here, that length, we'll call that A, and then the distance along the other axes, the vertical, we'll call that B. And so the area of an ellipse is pi times AB. Okay, so what about the ellipse that we're doing business with? Well, that's what we're going to figure out. So this distance from here to here is A, and that for us is 3. And from the center to the boundary vertically, that is a 2. Okay, so our final answer is going to be 2 times pi times 3 times 2. Okay. And that ends up being 12 pi. And we're done with that example. So now you know how to find the area of an ellipse. And folks, it's going to come up. I put this kind of problem on quizzes exams, and the final. Yeah, so know how to do it. Area of an ellipse, not too hard. You can do it. Good stuff. Okay, now for the advanced stuff for greens. Oh yeah. What do you mean? I thought we're already doing advanced stuff. Oh, you can do a lot of advanced stuff. Reminds me. Okay. So remember when we did greens and we had to do some preparatory work where we had to get a few definitions down. And so one of the definitions involved a simply connected region. We needed a simply connected region for applying greens. Yeah. And we needed a simple curve, and we needed to traverse around the region counterclockwise. Now I'll tell you a quick story. When I first started teaching this course over 20 years ago, a student asked me, well, what if I want to go around the boundary clockwise instead of counterclockwise? And I went, let me get back to you. So I phoned up my thesis advisor, my graduate advisor, Dr. Leslie. And I said, hey, Dr. Leslie, what if, we're using greens and, we want to go clockwise instead of counterclockwise? The student asked me a question. He goes, oh, well, I hear down in Australia, they do it the opposite way. He was a joker. Okay. Dr. Leslie, he still likes to joke around. Okay. And he was being facetious because in Australia, they still have greens the way we do it here. Okay. But he was alluding to the fact that when you flush the toilet above the equator, that would be us, the water goes in a different direction, swirling around if you're below the equator. Do you get the joke now? So if we flush the toilet and the water whooshes around counterclockwise, the Australians would flush their toilet and it would be clockwise. Okay, all right. If you're not laughing, all right, I'm not going to go and further explain the joke to you. But he was trying to be funny, and I just went, ha ha. And basically, the quick answer is that the agreement was greens is going to be considered, just sort of the standardized to make everybody on the same page, counterclockwise. They could have done it clockwise. Now, if you do greens and apply it clockwise, it's just going to give you the opposite in sign. That's all. Okay. But you agree it's going around counterclockwise. Okay. So going on that. Now, what about this simply connected? Notice that in this diagram where we're showing you different examples of not simply connected, one of them was a region that has holes. And it turns out you can apply greens on regions with holes, but you have to be a little bit careful. So we're going to do that now. And yes, it's going to be on quizzes and exams. Okay, don't go, oh, I'm going to fall asleep now because this is just sort of the advanced stuff. No. You need to know it. So what of it? So I'm going to show you the idea, the concept on why it is okay to have a region with holes, so long as you satisfy the other criteria. So check out this region here, and let's say it's got a hole right here in the middle. Okay, there's the hole. So this is how we roll. Okay, watch closely how I do this because it is kind of interesting. Let's say this is the starting point right here on the outer boundary. So we traverse the outer boundary in the counterclockwise way there, and we'll call that curve C1. Okay, so our overall curve, we'll call big C, is going to be C1 union some more stuff. So then what we're going to do is we're going to grab a knife. We're going to grab a knife and we're going to make a slit. We're going to cut a slit in our region right here with our knife. That is known as a slit. Okay. And so what we're going to do after we get done traversing the outer boundary C1, we're going to drive along the slit, and I'm going to call that C2. Once we hit the hole, we're going to drive around the hole in the clockwise direction. Oh, why clockwise? Well, one of the things that it said in the directions there for Green's theorem was you have to traverse the region in such a way that if you're driving around it, you can look over your left shoulder and you'd see the land. So I hope you can imagine that we have to drive around the hole clockwise, we'll call that curve 3, so that we see the land, this is the land here, over our left shoulder, okay? Now, once we get done going around the inside of the hole there, that's part of the border of this region, that's why we have to traverse it. Once we hit sort of where we started, we have to end up at the very same starting place. So we go back along the slit, I'll call that C4, until we get to home. Now, it turns out since C2 and C4 are really the same path, but they have different orientations, those line integrals will end up canceling each other out, because whatever the line integral along C2 is, the line integral along C4 will just be opposite in sign. So that's sort of gone. So we really only have to worry about C1 and C3, because C2 cancels the C4 line integral. Okay, now, well, how does that help for anything? Well, it just does. So let's take a look here at this next example. And then what I want to remind myself to tell you, what if you have 2 holes? So we'll do that, or 3. Let's do example 2 first. Okay, check out example 2. So how about your region is going to have a hole in it? It's going to be inside this ellipse, okay, but outside this circle. So if I draw the region, that ellipse is the same ellipses that we had before, I believe, that had a -3 and +3 as x-intercepts, and 2 and -2 as y-intercepts. Okay, and then a circle is a unit circle centered at the origin. So that's just this little circle inside the ellipse like this. And so the region is this, it's inside the ellipse, but outside the circle. So I'm shading in the region R. Inside the ellipse, but outside the circle. So it's got a hole in it, but greens can apply to holes now from what I just showed you. It's legit, provided you cut a slit somewhere, you know, we can cut the slit anywhere. We could cut our slit right here. It doesn't matter. Just assume you can cut a slit and just go for it. And so as long as you honor everything. So check this out. So this line integral becomes the double integral over the region dn dx minus dm dy. Yeah, you can do that. Okay, so let's go ahead and get dn dx minus dm dy. So m is 2xy and n is 2x plus x squared. Okay, so what are we going to do? Well, let's get dn dx. That looks like it's going to be 2 plus 2x minus dm dy. So the derivative of 2xy with respect to y is 2x. Now I hope you can see what's going to cancel are the 2x terms. Oh, cool. So what do I have? Well, I hope you recognize this. This 2 is just a multiple, so you can pull it out in front. And then you have a double integral with a 1 in the integrand. So this represents area. Area of what? Area of our region. What's our region? It's a special region because it's kind of looks like a squash donut. It's inside the ellipse, but outside the circle. Okay. So what is the final answer going to look like? It's going to look like 2 times area, but for us that 2 is going to be times the area of the ellipse minus the area of the circle, because that circle is a hole in there. So no problem there. We're going to go pi AB for the area of ellipse and pi r squared for the area of a circle. We're just going to use our knowledge of formulas. So we're going to have 2 times pi, and remember the a here was 3 and the b was 2, and the r here, it's a unit circle, so the radius was 1. So our final answer is going to look like 2 times 6 pi minus pi, but that's 2 times 5 pi. Final answer, 10 pi, and we're done with this problem. Pretty cool, huh? Everybody see that? Exciting stuff. You should be really like happy now. That sounds good, Esteban. What do you have in your chat there? Yeah, the illustration is greens over medium egg for his calculus breakfast. Oh, okay. Green eggs and
Yes, because all of those regions that you just showed us, it
Yeah.
looks like an over medium egg.
yeah, it does
So,
right here. Okay, so let's
yeah.
talk about what if you have more than one hole? Like, how would you deal with that? Or even 3 or 4 or 5 holes? No problem. The way you would do this, greens would apply. You would cut 2 slits here. Here's a slit, and here's another slit. And then you would traverse the outer border counterclockwise. That would be C1. And then you would approach the first hole along C1. And now watch this because it's really weird. And this will help you if you take an upper level math class. I'm not making this stuff up, people. You think this is like just child's play? Yeah, green eggs and ham. It's more than that. You're going to only go along the, excuse me, this is this hole here. You're going to go along the bottom of the hole. Oh, my pen is not up. You're going to go along here, and then you'll stop right here. Okay, we'll call that C2. No, we have C1 on the outer border, and then C2 along the slit, C3, and then we'll go along this slit, we'll call it C4, and then you go all the way around this hole. Remember, you have to go clockwise. We'll call that C5. You go back along this slit, the opposite direction, call that C6, and yes, C4 and C6 will cancel each other out. And then this hole here, you go along the upper semicircle in the clockwise direction, so that'd be C7, and then you'd finish to get back home by going in the opposite direction of C2, that'd be C8 to get back home. Okay, so that's how you would justify a region with holes, and then greens would apply if you had 2 holes there. Okay, cool, nice. Okay, so I hope you're appreciating some of this. It is somewhat advanced, but I like you to see it. So now to wrap up some of greens, let's talk about flux form. What the heck is flux form? Well, it's an alternative version of greens. And yes, you need both. Yeah, it's going to be coming up on this week's quiz. You got to know both versions of greens, as well as the last exam and the final. Okay, so what is it? What do you know already? So here's your version of greens that you guys already know. Okay, it's sort of the circulation form. Why is it known as the circulation form? And then this thing here is curl. We'll learn about curl Friday. The interpretation of this, when you actually figure out a greens integral, is the following. You can think of it as work done, but another way to think about it is this. Let's say you have a bunch of bathtub water, and the velocity of the bathtub water, you could think of maybe a jacuzzi, might be a better metaphor. The jacuzzi water is whooshing around, so that would describe your vector field. The velocity of all the water moving around in your jacuzzi. And let's say you stick a cute little paddle wheel in your bathtub or in your jacuzzi. And it's a special paddle wheel. It's got a little vertical axle and it's got a little axis. And then it's got these little paddle wheels that are vertical. And when you figure out one of these circulation line integrals or use greens to get it, the answer you get is telling you, it's measuring how fast and in what direction the paddle wheel is spinning. Okay, so if you get a positive answer when you do greens, it means that the little paddle wheel is spinning in the counterclockwise direction, and the larger the number, the magnitude, the faster it goes. And then if you get 0, that means the paddle wheel doesn't spin at all. It's just sort of sitting there in your bathtub. Maybe your bathtub is just still water, kind of boring. And if you get a negative number, it means the wheel is spinning. It's spinning in the clockwise direction. And the magnitude of that number would give the velocity of how fast it's spinning. Okay, there's another version of greens, though, that doesn't involve paddle wheels. It's got a different idea here. It's known as the flux version. And so it computes flux. Uh-oh, what's flux? Well, if you submerge your closed curve into your bathtub or in your jacuzzi, it would calculate the amount of water flowing out or crossing the boundary of your curve. Okay, and so what they do here to get this, instead of taking the projection of F along the curve with the tangent vector, you use the normal vector instead, because you want to get the amount of fluid flowing out instead of along the curve. So along the curve is the circulation, out is flux. So you want to pick a principal unit normal vector that is directed outward. And so you remember that the unit tangent vector and the principal normal vector, remember they're orthogonal to each other. Yeah, so if you're doing a 2D unit tangent vector, it's actually pretty easy to figure out which unit normal vector you need without doing all the calculations. So you just find your unit tangent vector, and then knowing that you want t dot n equals 0, your n could either be y negative x or negative yx. And so if you want to pick the one where you have outward flow, you're going to pick the y negative x. And then of course you unitize. So that's what we're going to pick. Okay. You're thinking what? What now? So they're just showing you here this diagram of how they're figuring all this out. So if you use Green's, where instead of F dot T, so we're using F dot N, because we're projecting the force field on the unit normal vector that's going out of the curve. So you're going to take a dot product. You got your force field, and then you've got that unit normal vector. Okay, and then this is the arc length element. Remember, that's r prime magnitude dt. And so what happens is these r primes cancel because you can distribute it. So then what you get is m times dy dt minus n dx dt dt. And then if you distribute the dt, these dt's cancel. And so you end up with m dy minus n dx. And that's known as an outward flux line integral. Okay. And so your new m is negative n, and your new n is m. So that's why you end up with the double integral of dm dx plus dn dy now this time. Okay, because you still want to take the derivative of whatever's multiplying with your dx with respect to y. Okay, so this is the alternate version of Green's. Okay, so what we're saying now is that, no, I don't want to sign into Adobe, but thanks for asking. We're saying that you've got this line integral, negative n dx plus m dy, like that. And that ends up being this double integral. So you're going to take this guy's derivative with respect to x minus this guy's derivative with respect to y, and then the minus minus ends up being a plus. And that's why you get that. Okay. So we are calculating the amount of water flowing out of your closed curve. So you can get positive, negative, or zero. If you get a positive answer for flux, it means there is more water going out of the curve than flowing back in. If you get 0, it means the amount of water flowing out gets canceled out by the amount of water flowing in. If you get a negative number, that means more water is flowing in than flowing out. Okay, and you're going to see that later on, we're going to do this in 3D, and that is going to be known as the divergence theorem. That's coming up next week. Exciting stuff. So this this vector field, dm dx plus dn dy is going to be 1 plus 1, which is 2. And so because that's a positive number, there's going to be more water flowing out of the curve than in. Okay, so let's do our final thing here, and then I'll do a big summary of Green's, and then we're going to be done with Green's. Oh, how exciting. Okay, so this is a similar problem to what I would put on a quiz or an exam. So focus up here. We want to find both the circulation and the flux using both forms of greens for this vector field. And the region R is going to be just a unit circle. Okay, that's easy. And of course, we'll have it, for the circulation part, we'll go counterclockwise. Okay, so let's do circulation. It's a really easy problem. You know everything now. When you do the circulation line integral, that's the mdx plus ndy line integral. So you're finding circulation, that's the paddle wheel. How much would my paddle wheel spin if I put it into my jacuzzi? That version of greens says, hey, turn it into a double integral, but your integrand is going to be dn dx minus dm dy. Okay, fine. So for this particular problem, here's your m, it's x minus y, and n is x. So dn dx would be just 1 minus, and then dm dy looks like that's going to be -1. Okay, fine. But we really have 1 plus 1, which is 2. So what do we have? We have 2 times this double integral. Now, what did we say about double integrals that have a 1 as the integrand again?
Area?
Yeah.
Area of a circle.
In this case, area of our region, which is area of a unit circle. Oh my gosh, I don't have to really set up this double integral. Cute. I mean, I could go, okay, 0 to 2 pi, 0 to 1, r dr d theta. That actually would be the double integral because I want to convert to polar. But I don't have to because I already know, I've got pi r squared here. And for us, the radius is 1. So our final answer is 2 pi. So because that's a positive answer, what it would mean is if we stuck our little paddle wheel into our jacuzzi back here, it would be rotating, it would be spinning, and it would be spinning in the counterclockwise direction. Okay, that's our circulation. Circulation. So now what? Well, let's go ahead and figure out flux. So if we place our little unit circle in our jacuzzi of bathtub water, where the velocity field is this force field here, how much water would be flowing out across the boundary? That's the flux. Or maybe we'll get a negative number, so more will be flowing in than flowing out. Who knows? We'll find out in a moment. Flux. So a flux line integral looks like this, m dy minus n dx. But don't worry, because you won't have to officially evaluate that, hopefully, because you'll just turn it into a double integral applying this alternate version of greens. This is the flux version for greens, where the integrand is dm dx plus dn dy. It's different, very different. Notice this here is dn dx minus dm dy, whereas this is dm dx plus dn dy. Very different, okay? And by the way, we're going to learn on Friday, this is the divergence of F. We'll learn that next time. Okay, so let's go ahead and get dm dx. Well, m is x minus y. So the derivative of x minus y with respect to x is 1. Now be careful, this isn't going to be the same. Okay, now dn dy, since n is just x, when you differentiate x with respect to y, big news here, it's just 0. Okay, but then this is just a double integral with a 1 as an integrand. Isn't this area again? This case, area of our unit circle. Yep. So you're just going to go pi r squared, and in this case, we just get pi. And because that's a positive number, that means more of the water is going to flow out of our circle if we placed it in our jacuzzi than would be flowing back in. That's what that number means. Okay, pretty cool, huh? So now, now I mean, and then we'll do the big summary of line integrals, okay? Got Captain Picard here. Spent a half hour parameterizing the curve for an obnoxious line integral. Realized the vector was conservative, so he could have used the fundamental theorem of line integrals and not have done any parameterizing. I love that meme. Okay, here's a big summary. This is not in any textbook. I made this up. You're welcome. It's the big summary of all line integrals. I'm very proud of this diagram. I hope you can appreciate it because it's going to summarize everything we've learned. in the last 3 sections. So take a look. Let's say somebody gives you a big old line integral to go do. You're like, oh man, what do you do? Well, follow my flow chart. Is it a type 1 line integral? So that would mean it's one of those scalar line integrals where you're using the line integral not to find work done by a vector field because there's no vector fields involved at all. You're looking at some density function and you're figuring out the mass of a wire. Okay, if that's the case, then whether it's a closed curve or not a closed curve, you're stuck. You have to go do the line integral, using brute force. And the curve has to be parameterized if it isn't already. If you're lucky, they already parameterize it for you. If not, And then please remember the ds. The ds here is the arc length element. Arc length element, very important you know that. And that's the magnitude of the velocity vector. That has to get involved when you do a scalar line integral. And your final answer is traditionally positive because it's supposed to represent mass. I've seen some textbooks where you do a scalar line integral, they'll have a homework problem where you get a 0. I'm like, no, I'm not okay with that. You shouldn't. Okay, now what if you weren't going along that path along your flow chart? You ended up with either a type 2 or a type 3, which means a vector field is involved. And either of these types, they're really the same because the type 3 is just somebody did the dot product for you of the vector field with the velocity vector. So if you have one of these types, you have a couple choices. You have to ask the question, is the vector field conservative or not? Okay, so let's say it is. So then you go down this path. Then you have to ask another question. Is the curve closed or not? If it's closed, hey, good news, no work needed. Just use the theorem for equivalent conditions. Hey, the answer is 0. I'm done here. Woohoo! But what if it's not a closed curve? Well, that's still not too bad because you can use the fundamental theorem of line integrals and you don't have to parameterize the curve or anything. You do have to go find the potential function. Remember that we talked about, that's go get mama, go get the potential function and apply the fundamental theorem. So all you need to know is the starting point and the stopping point because it's independent of path. And then the final answer may be positive, negative, or 0 because you're basically doing a work integral. And work can be positive, negative, or 0. Ask one of your physics friends. Okay, now what about if you're doing a type 2 or type 3 and it's not a conservative vector field? Okay, then you have to ask the question again, is it closed or not closed? The curve, that is. If the curve is closed, hey, go use greens. Yeah. And then your answer may be positive, negative, or 0. If it's not a closed curve, sorry, you can't use greens. And I'm even more sorry because you do have to do the line integral by total brute force. You got to parameterize if it isn't already and then do all that stuff. Although it is okay to go backwards in time, I'm going to let you when you're doing the parameterizing. Okay, and that's the big summary of line integrals. And so it basically says everything that you need to know. And yeah, we're going to be learning Stokes' theorem soon as well. I hope that you, when you get done with my class, you don't have what I call the flush syndrome. You know, after you take a final, this happens to a lot of students. They have what I call the flush syndrome, and they, flush everything out of their brain and they don't remember anything. That is not okay. Come on, remember some stuff in this class. Okay, that concludes today's lecture. Congratulations, you now know Green's theorem. Yay!